Thank you very much for this introduction. So this presentation is about Zset software, which is different from Forge suite softwares, and I will talk about the general presentation about our software, and also I will present an example of lifetime estimation of components on an example from Forge to Zset. So very quickly to start, I would like to tell you that this is a Zset, is a material and structure analysis suite, which is a collaborative project between several actors, very famous research institutions from Mainz, Paris and ONIRA, the French Aerospace Lab, and Transvalor. And so all of us, we share the same code, the same platform to develop our models, and we participate in common research projects. So if you want to visit us, don't go to Nice, please go to Paris. We are here. Our offices are in Paris. So when we talk about Zset, so Zset is a complete suite of tools which cover a very large panel of applications, starting from constitutive flows to structural analysis. We have tools for advanced post-processing, for damage analysis, and fracture analysis. So today I will talk about first three cases here, and I will leave the last one to my colleague Didier Soria from Safran to talk about fracture analysis on aerospace applications. So in this presentation I will mostly cover two topics: Zmat, which is a material library, and Zpost, and I will also show you an application of Zpost to Forge simulation. So Zmat is advanced material library. So you have a big collection of models which ranging from elasticity, hyperelasticity. We are very strong in plasticity and viscoplasticity for metallic materials, for very critical materials used in the critical part of aerospace industry, automotive industry. And we have also porous plasticity, shape memory effect models, polymer models. And all of these models were already used since many years in aerospace, car manufacturers industry, and energy a lot. So when we talk about Zmat, we imagine a collection of models. And actually, we don't think in terms of models, we think in terms of material bricks. And those material bricks identified on experiments. And actually, our collection is made of all these bricks, which we can, with the help of a very simple input file, combine together in order to obtain models. So our models, we build them dynamically in the input file, based on the observation that we have from experience. So if you want so you fill the input file, and then of course you have tools to drive this input file to obtain curves. So this one is a very typical curve for elastoplastic cyclic behavior. This is typical for automotive industry, aerospace industry, and so on. So on the right you see the cyclic loading, on the left cyclic loading, and on the right this cyclic response of the material model. So these models, of course, are used for TMF analysis, thermal mechanical analysis, and when we talk about thermal mechanical, we want to make dependent our parameters on temperature. So it's very easy in the input file. Again, you can put tabular coefficients, or you can put functions. And in this case, the simulation on the left shows you the response of the thermomechanical analysis in this case. So exactly the same model, but the coefficients are temperature dependent. And you see how it changed the behavior. So the material library is continuously developed. We add new features in the library. So for example, here for cobalt-based and nickel-based alloys used in aircraft combustion zone components, we developed new models, and you see some of bricks that we implemented recently for Safran Group. Also, I would like to say that, underline that most of our developments are published in, so you have publications for all of these models that we have in the library. Here you have, for example, a new family of pressure-independent yield criteria, which ranging from isotropic, anisotropic, and isotropic asymmetric criteria, and it's very important for aluminum alloys and magnesium alloys applications. One example of asymmetric behavior for cast irons. This is a very important material model for us. So it's used for diesel engines for marine and energy markets. So we work on with Wärtsilä company in Finland on those applications, and the material microstructure shown here. So because of this microstructure, the response of because of weights and the holes and actually porosity present in the microstructure, the response is not symmetric in tension and compression. It's very easy to take into account in the model, choosing the right yield criterion. Also another material model for gray irons. So this model is used for heavy duty machinery and diesel power plants. So the model includes all features that we want to use for these applications. So I talk about plasticity or viscoplasticity in this case, temperature dependence, straight rate dependence, but also we want to be able to represent the stiffening degradation in tension and re-stiffening in compression when we go back from tension to compression. So to be able to represent this region precisely. When we talk about materials, we also have to mention calibration, because without calibration our models are nothing. It's only equations. We have to put some parameters into the models. So we have to perform experimental tests, isothermal or anisothermal for TMF applications. What has to be underlined that the experimental protocol is closely linked to the model itself. So the model, for each model, we adapt an experimental protocol to fit the model. So here you have examples where our customers fitted our models on for their applications. On the left you have an example of lamellar cast iron material behavior calibration for TMF tests, and on the right you have an example of aging material for automotive industry, precisely for Renault company. So just to conclude about Zmat, Zmat is an advanced material library. So it's also it has to be underlined that it's easy to plug to finite element codes. So you put this material library, you run it with Abacus, ANSYS, and we work now on Forge as well, and you obtain your results. So here, for example, the results obtained with the help of our models in Abacus, you see on the right. And it's very efficient, and Zmat now can be called as material modeling and development platform. So now I go to the next part of my presentation, this is ZPost software. ZPost software is it's very important for us because it allows to estimate fatigue life of components. So first, software Zmat allows to calculate stress and strains precisely, so derive strain-stress loops of good quality, and then we apply this kind of approaches, post-processing approaches, to calculate the fatigue life of the components. So it starts from the data that we read from finite element solver. We apply some number of processes and we write the output in the format of the finite element solver. And what is the good news for the last version of Zset software, that we have reader and writers for FG3 format. So today we are capable to read fields from Forge and to write in the Forge format, and they will show you in the end how it works. So as you could understand already, we would like to provide collections of things, of features. Before it was about material models, here about post-processing. You have very simple and very complex ones in the collection. The most important for us is lifetime models. So lifetime models include specific elementary models to extract information from stress-strain cycles. So, for example, to find minimum, maximum range of stress cycles. It allows to calculate cycles. For example, here you have very complex history. You have to be able to calculate cycles, extract them, and calculate and distinguish between big cycles and small cycles. And also average sometimes responses to smooth surface gradients. You want to be able transfer field between nodes and integration points easily, because sometimes you have to bear from this information to focus on the hotspots in your structure. So we have a probabilistic models, creep models, fatigue for high cycle fatigue models and low cycle fatigue models, and very generalized model that we call ONIRA model, which is a Chabosh damage model, which includes which allows to describe both LCF and HCF regimes in one model, so the whole Verlick curve. And it includes multiaxial capabilities, allows to model mean stress effects. We discussed about it last time, 2 years ago, and the possibility of coupling damage, non-linear accumulation of damage on cycles, and also interaction with the environment, for example, oxidation. So how it works, you have an equation how to calculate the number of cycles to failure, and you have ingredients that come from the cycles that we calculated in the part, and then you put everything in the equation. You define some parameters to fit your model on the experimental results, and you run it. In the end of the day, you obtain the result, which unfortunately it's not a good. Maybe there is one slide missed, but okay. And you obtain the result, which can be projected directly on the structure. So point by point, every point can be post-processed independently. And so we obtain the results. So we will see it a little bit later. So now I will show you how these fatigue estimation tools can be plugged to forge computation. So here you have a forge computation. What we are capable to do now is to read forge results and to convert them to Zset for further post-processing. We apply any types of models, but in this example it will be lifetime model, and then we export the results in FG3 format for visualization with your post-processing tools. So this is how it works, and this is the application. By the way, I would like to thank Gregory from Transvalor for his help to set up this example. This is about connecting rod hot forging, and I think it's a quite typical example from your database. And so what we wanted to do is to use this example to calculate number of cycles to failure of these forging tools. So which is quite important in your work. So on the result were imported in Zset, and if we look, we have on the result you have one mesostress evolution on the left, and you have temperature evolution on the right, and those ingredients you can introduce them in the fatigue model for fatigue lifetime estimation. So the way how we do it, we will, with help of ZPost, we can very easily find what we call critical points. We can calculate the find the points where you have maximum stress variation or maximum stress, maximum temperature variation, or maximum temperature globally in the structure. And also we can apply the model, fatigue model that I presented just before. So the model that we choose is presented here. So it's completely created by us. It's an artificial model. It's just to show how it works. So what it shows that the four stresses that you have here, for example, 600 megapascals, you have this lifetime. And for 400 megapascals, you have a longer lifetime. And for example, 10 megapascals, it's infinite lifetime. This is what the curve shows you. And this curve were created for several temperatures to take into account temperature dependency. And we applied this model on the results read from Forge simulation. And when we post-process them, we visualize them, we can have access to this kind of fields that you see on the right, and it shows the number of cycles to failure projected on the mesh. Okay, so red zones, it's opposite to it's not a critical, it's actually the most safe zones, and the critical zones, they have a less number of cycles to failure, and they highlighted by blue colors here. Okay, and what is the nice new right now, that exactly the same model can be exported to FG3 format and be visualized with your with the viewer, NXT GUI viewer. And so here you have access to all tools available in the viewer. So you can of course see these views, but also perform cuttings, look inside. And we didn't have enough time to post-process it for this presentation, but what is interesting to see that inside of this, if we cut this part, and inside we have a channels of critical zones that go inside in the volume and not only in the surface. So the model is very powerful, allows to provide a lot of information about how your model degrade with the usage. So I think this is the last slide of my presentation. Just to recall what I was talking about today, Zmat. First part, it was about Zmat. So we have a very huge collection of material models, so please do not hesitate to use it for your applications. And we also provide Zpost, which is a generic tool for data post-processing. Today is compatible with FG3 format for import and export. We set up a simulation chain for fatigue lifetime analysis of forging tools, but it can be any type of simulation. You have now the possibility to visualize Zpost results with NXT GUI. Thank you very much for your attention.
Thank you very much, Nikolai, for your presentation. We have time for some questions.
Thank you for your presentation. Alexis Gaillac from Framatome. Can you explain a little how does it work, the link between Zmat and Forge? We can define kind of user materials with the Zmat?
It will work. I told it during my presentation that it's not yet ready, but we are working on that. We have some issues until now, and so the idea is to use the same thing. I can go back to my presentation maybe very quickly. So here you have input file. It will be exactly the same approach that we use for Abacus Senses and other software. So you will have an input file for Zmat, and Forge provides a user interface. You know about it, so you can already implement user material models in Forge. So we use this interface to plug our Zmat models to Forge. So this is the idea. So when they will work together. Forge will be responsible for structural analysis, for global equilibrium, and the Zmat will perform local integration of the material law. Okay, and they will exchange information on every step and for every element and the integration point.
Okay, thank you.
Okay. Any other questions?
I'm Murat from Unatus, and thank you for your presentation. Except for the input parameters for calculation, does Zset needs any other third-party software?
That's a very good question. So yeah, Zset has very many. Actually, our models can work independently or together, and it can work independently. So be plugged to external codes, but also together in the one calculation chain, and this chain can be based on our own native solver that we call Zébulon. So we have our finite element solver also. So some of those simulations were done with Zébulon, which is our own finite element solver. Okay. So when you buy Zset, you have a choice to buy Zset, Zmat for Abacus, or Zset native standalone. In this case, you will have everything.
Okay. Any other questions? So thank you again, Nikolai, for your nice presentation.